So here we are, finally, to Newton's third law. To every action, there is always opposed and equal reaction, which is actually pretty close to what you probably know it as, is to every action, there's an equal and opposite reaction, which is basically the idea. So this has nothing, it has to do with forces, but it's kind of unrelated to motion the way the others are. But it's basically the idea is if I have two objects touching, like, I'm just going to leave it as like two marbles, I guess. If this marble is touching that marble, then the other marble is touching it back. You're like, thanks, Newton. Duh. No, but this is like really important. And the reason it's important is it matters in how you draw the circles. Okay? So if I'm saying that this ball is pushing on that ball, then this ball is actually pushing on that one. Okay? Because the idea is, even if they are touching, it kind of comes to the idea of internal forces. And that's the only way I can really make sense of it, is if I put them together, and I now wanted to look at the system of the two marbles together, those are now internal forces and they cancel each other out because they're part of the system. Even if I included them like in the sum of the forces in that direction, they would cancel each other out. Okay? Or similarly, if I was like, well, this ball is magnetic, so it's pulling on the other ball, and it'd be like, no, that ball's pulling on that ball. As long as whatever you do to the one, you do to the other, but you draw it in the same direction. And if you label this one X, you label this one X. If you label this one chicken nugget, you label this one chicken nugget. So that's really what this is all about, is that, I don't want to say it's philosophical, but, if my head is sitting on my shoulders, I got a blockhead for some reason. So whenever I look at, a body, if I'm doing a free body diagram of a person, I'm not really separating their head from their shoulders, but I could, and if I did that, it would be like, come here. It would be like, okay, so the shoulders, or the neck, I guess, is preventing the head from going into the body. So this is normal force to the body. But then in return, I have to, once I separate these, once I pull these apart for the purposes of drawing the picture, they're not apart in real life. They're touching in real life. And I think that was the thing that I never really got about Newton's third law, is that they're touching in real life. So this was really here, like this, okay? If I'm pulling them apart to analyze them separately, I need to acknowledge the fact that they were touching each other. And to do that, I need to make sure that however I draw the arrows, I have to draw them correctly, but they need to be the same. Because if they're not the same, like let's pretend that this one was 30 and this one was 20, then if that force is 30 and that force is only 20, then that means my head is literally flying off my shoulders. And I know it's not. I know my head is stuck on my shoulders for the moment. Does that make sense? I know my head is, I guess, on my neck. But this is like the thing, is that that's why this has to be 20 or else they're not touching. I guess that's as easy as I can describe it. I've really struggled with how to teach free body diagrams over the last years of 15, 17, lots of years of teaching engineering. And I just have seen some people that get it the first time and they're like, why do you spend so much time doing this? And I'm like, because this is what I always messed up. So the idea is that if I put those two together, the n equals 20 up, like if I took the sum of the forces and I just looked at these, I've got plus 20, minus 20. So like there's no relative motion between the head and the neck. They're not moving with respect to each other. If I was just floating in space and there was this force, they would have to be the same force, I guess. So they have to be moving at the same speed. Well, what if I'm nodding your head? Shut up. Okay. So whatever these are, that's the equal and opposite reaction. And this is really helpful because what happens is you'll get a problem like this. It'll be like, here's a block and here's a block. And it'll be like, this block is block A, and this block is block B, and this one is 30 pounds, and this block is 50 pounds. Okay, so if I'm drawing a free body diagram of the block set, and the block set is on the ground, then I know that the weight of the set is 80, and there is a normal force from the ground preventing it from going into the ground. So normal force from the ground. And because I'm really good at math, some of the forces in the y minus 80 plus ng equals the mass, which would be 80 divided by 32.2 times acceleration in the y direction, but in this case, that's 0 because the boxes are not flying off the ground. So my normal force on the ground is 80 pounds. Okay? Now, this is important and like legit important and also legit confusing. But I feel like if you just take it all in at the same time, it maybe makes more sense. So now what I'm going to do is I'm going to draw two new free body diagrams where I'm going to draw just B and then just A. Okay? This is important. Okay. B weighs 50 pounds. And A weighs 30 pounds. Okay? Now, the box here is touching the ground. I knew that. But the two boxes are also touching each other. So the way that you can kind of respect that is you can say box NA has a normal force on B, and then the equal and opposite reaction is the normal force from B to A. But they're I'm labeling the same variable, NAB, because they have to have the same value. If they don't have the same value, then the blocks are flying apart or squishing into each other. Okay? So if you look, if I combine the two like this, see how the NABs cancel out? If I was doing the sum of the forces on this picture, I'm going to leave it like that for a second. If I did the sum of the forces on that picture, I'd have minus 80 minus n. Actually, I'm just going to write it and then I'll have to hit undo. So if I was going to do the sum of the forces on this picture, it'd be minus 50 minus 30 minus NAB plus NAB plus NG, except I can't spell, NG equals 0, because I know the acceleration is 0. So do you see these cancel out? And I still have 80 NG equals 0, which is the same thing I have here. Okay? That was like the brilliance of Newton, is realizing that when you pull these things apart, those have to be the same because the internal forces have to cancel out. And if they don't cancel out, there's all kinds of other weird things happening, and now we're not doing Newtonian mechanics anymore. Okay, so now I'm going to undo a whole lot to get back to where I wanted to be. Where's where they were separated? So I'm trying to prove to you that Newton was right. Oh, I can't undo anymore. Okay, I guess I gotta just redo this whole stupid picture. Okay, so what did I have? I had this picture, and I had this picture. I'm just gonna have to redo it. That's okay. It's good. My mama say, put hair on your chest. So I have B on the ground, and I have A up here. Okay, you're like, I already did this. I know. Life is hard. Pink. Okay, so this was what, 50? And there was a normal ground, and this was 30. So I usually do all those external forces first before I forget them. And then I'm like, okay, but they're touching here. So this guy can't go through the block below it. That's preventing motion through the block below it. So since I did this one up, I have to draw this one down. Now, if I've done this right, I should get the same answer for both sets of equations, but let's make sure. All right, so if I do this for the system, for block B system, the sum of the forces in the y is minus NAB plus 50, nope, minus 50, plus NG, and I'm just going to write, you know what, I'm not, because this is the mass of this block is 50 over 32.2 times acceleration of block B in the y direction. Okay, so I'm glad I didn't skip over that because that's important. So this is just for block B, so that's the acceleration of block B. Now I happen to know that the acceleration of block B is 0, so that didn't actually matter, but there is a universe where this could have mattered. Okay, so I know that negative NAB minus 50 plus NG equals 0. And I'm like, dang it, I can't solve this problem. And you're like, well, you already solved this problem. I understand, but like, just, okay. There's a reason we're doing this, I swear, because eventually we're going to get to problems you can't just solve without taking them apart. Okay, now I'm going to do this for block A. So the sum of the forces in the y are minus 30 plus NAB, and this is equal to the mass of that block A times the acceleration of block A in the y direction. Acceleration of block A in the y direction is still 0, so I don't care, but that's great because now I have negative 30 plus NAB equals 0, so the normal force between the two blocks is 30 pounds. So the normal force between the two blocks is 30 pounds. So now whenever I plug this in, sometimes students freak out and they're like, what do I do about the negative? This is literally a variable. This is like x. X is 30. So you don't worry about, you're like, that's literally negative x, negative 30. Okay, you just literally plug the value in. Try not to overthink it. It is actually very hard not to overthink these things because you start getting in your head and then your brain convinces you that you're doing the wrong thing. But look, I got the same answer. This is actually a huge deal, and that's what Newton's third law is all about, is that, you know, we can break things apart to find out what is happening between things. And why would I care? Eventually, in a minute, I'm going to care because frictional force depends on the normal force between two objects. So like the frictional force, if I was like pulling on this or something like that, whatever frictional force is going on between A and B is going to be different than the frictional force going on between B and the ground because there's more weight on the ground. And you're like, but I could have just known this. Okay, well, you know what? Good for you. But I guarantee you I can give you a problem that'll be hard enough that you can't do that without understanding the basics. So like there's this ridiculous problem we have in statics where it's like a guy standing on a beam, and for some reason it's dude standing on a beam and he's holding a string on a pulley. Okay, maybe he's, and then the pulley's like, I'm not explaining it very well, the pulley's like connected here, and it's like, how much tension is in the pulley? I don't know. It's a really dumb problem, and every time we look at it, we're like, why is this guy doing that? Or maybe the thing's in the middle, or it's not in the middle, it's maybe here, and he's pulling on it. Maybe that makes sense. So it's like, what's the tension in that? And it's like, well, okay, so you've got the weight of the beam, and then you've got the tension, so you could like draw the free body diagram of the doop, and it's also pinned to the ground, and it's got dude standing on it, but then, you know, the dude standing on it, that's a normal force that gets counteracted here, but then you have the weight of the guy, but then you have the tension. And anyway, so it gets harder is where I'm going with this, so don't just blow off the easy problems because you get a feel for it, and you're like, I can just tell what the answer is supposed to be, because eventually you're going to get problems that are too hard to just feel your way through, if that makes sense. So there we go, and that's basically what they're saying here is the weight of the object and choosing the correct system. Okay. Yeah. So I'm going to do this whenever we... Hold on, let me see. Okay, yeah, I don't like this free body diagram either. All right, so chick pushing cart. Person pushing cart. And they're on the ground. Okay, so they're walking forward. This is kind of like the dude pushing the box in the train or the whatever. So what do we know? We know that the equipment, the cart is 12, her mass is 65, so her mass, or her weight, is 65 times 9.81. So the weight of the girl is that. The mass of the cart is 12, and the mass of the equipment is 7. So let's just put the equipment here, because it doesn't matter. So the mass of the cart is 12 times 9.81, and the mass of the equipment is 7. And then it tells us down here that the cart's wheels and air resistance are 24 newtons, apparently. I don't really know what they're trying to do with that. Hold on, let me see if I can understand exactly what they're saying here. Okay, I'm going to be honest, I'm not 100% sure what she's asking here. So I'm just assuming that they mean that the friction opposing on the wheels, it says in the cart's wheels and air resistance is 24. So I'm just going to assume that this cart has a friction of 24 opposing the motion. So these are all newtons now. So this is weight of equipment and weight of the cart. Okay, so obviously this isn't, right now the way this picture looks only works if the whole system is decelerating. Okay, clearly not decelerating. So in order for it to be accelerating the other direction, we know that, see, as her foot, we need her foot to keep her from slipping backwards. So this is the friction on her foot. Okay. She also has a, let me do this, a normal force, I didn't draw these, a normal force of the girl on the ground and a normal force on the cart and equipment. And I think that's everything. Okay, so let's check. I guess I don't know why I put those in a different color, because that's confusing. It makes it seem like there's something that they're not. So F, foot, this is friction, foot. Also, there's normal force of the girl and normal force of the cart and the equipment. So let's just kind of check. Do I have forces that make sense here? So she can't fall through the ground because there's a normal force preventing that. The equipment and the cart can't fall through the ground. I know that the friction of her foot needs to be greater than 24 to make her go forward. Don't actually know how they want me to solve this, but I'm going to play a game. Did they give me any other information? Oh, the professor exerts a backwards force, I can't read the problem, of 150 on the floor. So that means, I'm assuming, that it's saying a backwards force, but that doesn't make any sense. That the frictional force has to be going forward, so I don't know why it said that. It's 150. There's 150 feet. I don't know, why does it say a backwards force? That's so weird. Because if your foot is here and it's trying to slip, your foot's going to slip this way, so the frictional force has to go this way to oppose the motion. But I guess what they're trying to say is something else, which is fine. So I'm going to solve my problems my way. If you solve the problem the book way, you know what? We'll all be happy and it'll all be fine. So what I can do with this is now I can do, let's look at the sum of the forces in the, what do you call it, direction? Let's do the sum of the forces in the X direction. So there's 150 going forward, 24 going backwards. Now, for the mass, since I'm looking at the whole system, I need to go, the mass is 65 plus 7 plus 12 times the acceleration of the system in the y direction. Now, because the system is all moving at the same speed, I can just use that acceleration for everything in the problem, and that would be fine. So I have 150 minus 24 divided by 65 plus 7 plus 12 is 1.5. So the systematic acceleration in the y direction is 1.5 meters per second squared. So she's accelerating that many meters per second squared. Is there anything else we can do with this problem? Well, what we could do, in case you care, is since we know her weight, if we just do the sum of the forces in the y on the girl, so I'm just going to specifically do just the system of the girl. Maybe. Yeah, let's do that. And I won't do it in y. I'm actually going to do it in x. So she is pushing on, since this is Newton's third law, since she is pushing on the cart, there's a normal force between the girl and the cart. So the cart has to be pushing back on her as a normal girl to cart force. Okay, so you see if I combine those, they go away. But if I'm trying to look at her as her own system, once I kind of make that cut, I expose those internal forces. Now this is not going to be terribly interesting. But so what I could do here is I can say, well, the sum of the forces in the x direction are 150 going forward minus the normal force between the girl and the cart, and that equals mass times mass of the girl times acceleration of the system. Why did I write y direction up here? Y'all need to pay attention. Yell at me more. X direction, x direction, x direction. The system in the x direction. Now I know her mass by herself is only 65, and I know the acceleration is 1.5. Now this is in kilos, meters per second squared, so I'm going to get newtons. So I can now say that the force between the girl and the cart is 150 minus 65 times 1.5 times minus 65 times 1.5. So 52.5. So she's actually only pushing on the cart. Is that what I meant to say? No, this minus goes over there. Yeah, 60 minus that. So the force between the two of them is 52.5. The cart is pushing back on her at 52.5. Does that make sense? The cart is giving her 52.5 angstinesses. Okay? And let's make sure this is mathematically correct, because this just feels weird. But I'll bet you anything it's going to turn out okay, because I have faith in math. All right, so let's just look at the cart. If we look at the free body diagram of the cart in the x direction, the girl is pushing on the cart. There is a NGC in the positive direction, and there is negative 24. And that has to equal the mass of the cart and the equipment, which is 7 plus 12 times the acceleration of the system in the x direction. And then that is still that 1.5. Okay, so let's see if I get the same answer. And then I'm going to see if it makes sense. I always struggle with getting the answer and walking away being like, well, I got the answer, yay. And then stupid engineering makes me have to actually think about why the answer makes sense or doesn't make sense, and then I'm like, but I don't want to know. I just want to do math and be happy. So that would be plus 24. Oh my gosh, it's 52.5. Okay, so what does this mean? That means that if I was going to, instead of using her arms, or let's put it that way, her arms are in 52.5 newtons of compression to keep that acceleration going. So like if this was her and this is the box, and instead of her, if she just had like, I don't know, a spring or a piece of wood or whatever, this is feeling 52.5 newtons of compression as she is pushing that. So like if her arms can't handle 52.9 newtons of compression, her arms will snap. That was really gory. But I hope maybe made sense about why these calculations are important. Because everything is mathematically consistent, and that is like the coolest thing ever about Newton's third law. And I don't even know what they're doing with this problem. They just stopped there. But, there, they did do it. That is the force between the, what was the question? Calculate the force that compresses. Oh, look at me. I'm so amazing. Okay. All right. Kind of the same thing here where you've got the blocks, where you can either treat the blocks as a whole. So we have a force in 2 blocks. I'm just going to draw it out for funsies. So we have a force in 2 blocks. And I'm just going to, does it tell us masses or anything like that? I guess it's 2 and 6. Okay. So this is 2 times 9.81. This is 6 times 9.81. And what else do we have? Is it smooth? Frictionless surface. No friction. And 2 blocks are at rest. And then a force is applied of 24 newtons. And find the acceleration of the blocks. So this would be a thing where you can start off, let me also draw my normal forces. So I have a normal force for the first block and a normal force for the second block. And so without too much angst, you can be like, some of the forces in the x is 24 equals mass times acceleration in the x direction this time of the system. So acceleration is 2.4, right? 24 divided by 8, is it 2.4? They don't actually give the answer. Oh, that's the check your understanding one. Okay, we'll just assume that that's right. Okay, but now if I'm going to draw them apart, if I'm going to do this, if I'm going to separate them for the purposes of seeing, well, what is the reaction force between the two of them, I have my 2 little pictures here. So I've got block, 2-pound block, or 2 kilogram block, and 6 kilogram block. So all those forces I drew before still have to be there, because nothing has changed. The 24 newtons is still there. The 2.9 times 9.81 is still there. The 6 times 9.81 is still there. The normal 1 is still there. The normal 2 is still there. So I had 1, 2, 3, 4, 5 external forces before. I still have those 5 external forces, but now the difference is 2 was pushing on 6, so there was a normal force between A and B, and then there was a normal force between A and B. Now this is where you might freak out. If you, for some reason, draw the arrows in the wrong direction, it'll actually be fine. You'll just get a negative answer, and that means you drew your arrows in the wrong direction. That's a secret from statics that we're not going to get into too much here. I'm just letting you know. Because if you draw your friction arrows wrong, then things can actually go wrong. So we're not going to just start normalizing drawing things in the wrong direction. But if you're going to draw something in the wrong direction, this is one that's actually okay to do it. Because pushing on something with a negative force is the same thing as pulling on it with a positive force. Pushing on it with a negative force is the same thing as pulling on it with a positive force. Let's assume that that's what I meant to say and that it was right. Okay, so now if I'm doing the sum of the forces in the x direction for block 1, I have 24 going forward normal going backward, and that equals mass times the acceleration of 2.2. Okay, so 24 minus 2 times 2.4, so 19.2. Oops. NAB equals 19.2, so that's the force between them. And I should get the same answer both times, except here I really can't do any, well, I guess I could, here. Because near here, the sum of the forces in the x direction is just NAB. His mass is just 6, and the acceleration is still the same, because they're moving together as a unit. Things can get more complicated in different classes, you know, because it'd be like they're together, or they squish, or they something. So normal AB is 6 times 2.4. Please let it be 19.2. It's not. Did I do something else wrong? You know what I did wrong? I added 2 and 8. And this is how I find errors in my stupidness. Because I said 2 plus 6, and then I wrote 8. And then, okay, you know what? We're going to fix all this. I'm going to even put in a note this time that says, this person is stupid and should never be allowed to post things on the internet. But I don't think it's a rule that you're not allowed to be stupid to post things on the internet. So I'm going to try this again. 24 divided by, you know what? I don't even trust myself anymore. 2 plus 6 with a dot on it. 14.4. Okay, let's see if I can get this again. Whoa, that seems really high. Oh, because I didn't actually hit enter. 3. Okay, I'm going to take a break after this video. Okay, 2 times 3, so 24. Minus 2 times 3 is 18. And so this one should be NAB minus 6 times 3. And yeah, that is 18. And so now it's all consistent. Yay, I win it not being absolutely terrible. But I promise I'm going to go take a break now. And this has been a really long video. So you should also go take a break because holy jamalama. I'm hoping that by the time we get to the second part of this lecture in chapter 5 that it's going to be like, oh yeah, we already did all this. And it's just going to be me working out additional problems for fun and, I was going to say fun and profit, but not a lot of profit going on here, but just for fun. All right, have some good times with that.